Okay, now that you know how to translate from English into the language of first order logic so that we can express claims about the properties of individuals and objects, the kinds of things we couldn't fully capture in the language of propositional logic from the first half of class, we are ready to prove that arguments expressed in this language are valid, or not, as the case may be, although we won't use the proof method to show an argument is invalid. We will develop another method for doing that. That's a lot like the counterexample method we learned in week 1. So first point is that we're going to use a lot of the knowledge and skills we developed in part 1 of the course. So all the rules that were relevant in constructing proofs before, modus ponens, modus tollens, disjunctive syllogism, conjunction, simplification, constructing a conditional proof or an indirect proof. All of those are still relevant here. We're going to need additional rules to deal with statements that have quantifiers, statements with the little upside down A, for all X, everything has some property, or statements with a little backwards E, some things have a property. So that's what we're introducing in this chapter, a couple of rules that relate to quantified statements. And then everything else is going to look basically the same as before. Let's just get into an example. So here's the one from the textbook, and it actually doesn't matter what the predicates and the names stand for any interpretation of our predicates and names. This is a valid argument, but this is meant to express the argument that all humans are mortal. Aristotle is a human, thus Aristotle is mortal. So how will the proof go? Well, our new rule says that if we have a universally quantified statement, the main operator is the universal quantifier, then we can, on a new line, remove that quantifier and replace each bound variable with any object from our universe of discourse. In this case, we want to make a claim about Aristotle, so we'll replace it with A for Aristotle. So basically just copy whatever it was, we'll remove the quantifier, and we'll change the bound variable to anything from the universe of discourse. Now you have to replace the X's with the same thing. You couldn't just replace this with like this. It has to be the same thing. Whatever X was, now that A is what we put in the slot. And we're going to call this rule, unfortunately, because it's really long, universal instantiation. And we'll cite the line we are applying the rule to. It's because line 1 is true, and this rule says if we have a universally quantified statement, we can put this on a new line. That's the justification for putting this on a new line. Universal instantiation is kind of a mouthful, so feel free to abbreviate it as long as it makes sense, UI, or because I'm going to introduce you to a proof checker, an online proof checker, you might start to use, unfortunately, different names for the rules. For example, you might call this rule universal elimination, as in there was a universal quantifier and we eliminated it. We wrote one without it. So this is also called universal elimination, or just AE. A for the universal quantifier. It would be nice if it was upside down, but since that's annoying to type in, even in the actual proof checker rule, it says just write this. So let's just call universal instantiation AE. We've eliminated the A operator, the quantifier. Okay, so that's how we get this on a line. And now, what does the rule modus ponens say? It says, if you have a conditional statement, and we do, this is the main operator, it's a conditional. This is the antecedent, this is the consequent. If you have a conditional statement on a line, we do, and you have the antecedent of that conditional, exactly the same, whatever it is, and we do, then you can put the consequent of that conditional on a new line. So there's really no change here. It's just the antecedent and consequent now look different, but the rule is exactly the same. So we'll put the consequent on a new line, and then we will justify that by citing the two lines and modus ponens as usual. And it turns out for our proof checker, you can either write out modus ponens, and likewise, you could write out universal instantiation in a proof checker. You can write out modus ponens, or you can use this new abbreviation. That's the arrow, and this means elimination. So notice that when you apply modus ponens, you're eliminating, in some sense, the conditional symbol. You had a conditional, and now you have a statement that doesn't have that conditional symbol in it. You just have the consequent. So that's called elimination of this symbol. What did they call the modus tollens? Modus tollens just it's called MT. So this isn't like a very consistent naming system, but there you have it. That's the complete proof. The only quibbling here is what to call the rule that we used and how to make it so you can use a proof checker. I'll show you how this works later. So that's the rule. That's the complete proof. Our new rule is just this one. Does it make sense that we should have this rule? Recall that all of our rules so far, everything from part one, our rules embody valid inferences. Valid means if the premises are true, the conclusion must be true. If whatever you apply the rule to is true, then the thing you get from the rule also has to be true. Does it make sense that if this is true, this would have to be true? If you know that every single thing in the universe of discourse is such that if it's a human, it's mortal, then any single thing you pick, whatever thing, it doesn't matter, will also be the case that if it's a human, then it's mortal. That's just what all or every means. So that's why this rule preserves validity. If it's true that everything really has this property, then Aristotle has it as well. Okay, let's put this into the proof checker now. I said there's a proof checker. Let's look at how it works. Okay, first and foremost, it checks proofs in propositional logic and first order logic. We'll start using it now in part just because the proofs are a little more complicated, and as proofs get more complicated, there's more than one good way to do them, and I also didn't want to introduce a lot of stuff at once, but if you think I should have introduced this earlier, feel free to give me feedback, and maybe in the future I'll consider showing students that there is a proof checker for propositional logic and how to use it. Okay, so you have to select which one, and if you put in the premises and conclusion and it tells you they're not well formed, double check you selected first order logic. I'll show you what it looks like if you have it in the wrong mode. So let's start just by writing our premises in, and we'll separate them with something, a comma or a semicolon. I could just copy and paste this for all x, hx, then mx, but let's just look at our key here and type it up. So here's the notation for how to type in your premises and conclusion. It says for universal quantification, you can either use ax like this, or you could put parentheses around it, no upside down a. So let's write for all x, and let's just leave the parentheses off. Why not? We haven't been using them all along, so let's leave them off. For all x, if x is a human, what's our symbol for conditional? Just this. And it doesn't matter whether there's a space or no space. Then is mortal x. So again, you put spaces here or not. You could also put parentheses around the A like this. That's optional either way, but these parentheses are definitely required because they tell you the scope of the operator, that these variables are bound. Okay, so that's our first premise. And our second premise is that Aristotle is a human, so human Aristotle. And the conclusion is that Aristotle is mortal. And if I have it in propositional mode and I hit create problem, it says this conclusion is not well formed. So let's put it in first order. And now it's set up the problem. So as you can see, a proof checker doesn't tell you how to do the proof. It tells you if you did the proof, it's correct or not. And it'll give you some indication of which lines are correct and which aren't. So let's start a new line. What's our first move? Our first move is to use universal instantiation. What do? We basically can just copy this bit, but it might not accept that. Let's try it and see, because it says to use this and it doesn't say you can use an arrow. Okay, so we took off the quantifier and now we have to replace all of the bound variables with a name, one and the same name. Or term, one type of term, one thing that can go in the slot where there's a variable, the hole in a predicate, the blank in a predicate. Anything that could go in the blank of a predicate is a term. Names are the easiest to understand term. I left a comment on the text in Perusall with details about what exactly a term is, if you're interested in the minutia. Okay, so this is what we'll write, and now we have to justify it. We have to cite a line. That's the line we're looking at. And we have to, as always, cite the rule. And you can either type out universal instantiation, or you can just type capital A, capital E, and yes, it has to be capital. Let's just show what happens if you don't type capital. Okay, so I did this. Now I'm going to write new line, and it kept what I wrote. And now I say we can derive the conclusion, MA, Y, 2, 3, and let's just write MP like we've been doing and see what happens. Okay, let's check the proof. Okay, it's being real slow. Sorry, there were errors. Can't parse the justification. When it says it can't parse the justification, it means it doesn't understand what you put in because it is very specific about what means what. So we can go back and edit it. Let's make it capital because it says down here, universal instantiation, use capital AE. You can also write it out fully or just do this. Okay, and notice it wrote it out for us automatically. And MP, it doesn't say you can use MP. It says you can write out modus ponens or you can write this. Let's just write the short one. And notice it turned that into modus ponens. Okay, so now let's check the proof. Congratulations, this proof is correct. Let's start a new proof. Let's make it exactly the same for all X. If X is a human, then X is mortal. And Aristotle, wait, let's make that a premise, comma, Aristotle is a human, conclusion, Aristotle is mortal. Oops, it's not well formed. It has to be in first order again. Unfortunately, it doesn't just put it in whatever you were last in. And let's try making an error. So let's say we apply universal instantiation, but this time we don't consistently replace the blank with the same term. Let's say we do this, and we'll go line 1, AE, and then on a new line, we'll write MB, and we'll write 2, 3, modus ponens, or arrow elimination. Check proof. Sorry, line 3 is not a proper application of the rule of universal instantiation for the lines cited. So you can't use the rule like this. It'll tell you that. So that's a useful thing to have as the proof gets more complicated. Let's do some more practice. Here's another one. I recommend that you pause and see if you can already do this one on your own, and maybe even pause and try it in the proof checker on your own. All right, let's do it together. First of all, I don't have the premises numbered. That's an important step. Okay, so where do we start? Obviously, the rule that we're using is universal instantiation, which says basically, if you have a universally quantified statement on a line, and you do, or rather a universally quantified formula, it doesn't have to be a sentence, it just has to have this as the main operator. And you put that on a new line, and then you remove the quantifier and you replace all of the bound variables with one in the same term. Now, let's say this is a two-place and you have an unbound variable in here. You apply universal instantiation just the same, but you only replace the bound variables with the term, not the unbound variable. Okay, so we'll remove this. And so these are no longer necessary parentheses. And let's replace x with t. And our justification for this is line 1. And let's be lazy and write the shorter version of the rule name. Now what can we do? We're trying to get to t is a c, or t has property c. What do you see? As usual, I recommend that you pay close attention to the main operator or main quantifier in each sentence. So, for example, we have some main operators we can highlight here. What do we see? Well, when the main operator is a conjunction, the simplification rule applies. We can always take apart conjunctions. And when the main operator is a horseshoe, there are two rules that apply when what you have is a horseshoe, and that is modus ponens and modus tollens. So never a bad idea to just start taking apart conjunctions. So let's do that. And this is going to be line 2 simp. We can only apply it to conjunctions, reminder. And just put whatever those conjuncts are on a new line. So that's 2 simp. Now what? Well, we have a conditional statement. The antecedent is t is a p, and we have the antecedent exactly as it is on a new line. So we can put the consequent, whatever it is, on a new line. But now those parentheses aren't necessary. You can leave them if you want to, but they're not necessary anymore. And we will justify that by citing lines 3 and 4 and modus ponens. Now what do we have? Notice we've got some main operators that we could highlight here of new pieces to work with. What rule applies when your main operator is the wedge, a disjunction? Disjunctive syllogism. And do we have the negation of one of the disjuncts, one of the parts? We do. So we can use ds to get ct, and we will justify that lines 5, 6, ds. And that's the complete proof. So look at how this was really just what you already know, with one new rule about what must be true when a quantified formula is true. Okay, let's put this one into the proof checker. So I just copied and pasted that, and I never did check the arrow to see if it accepts an arrow, or if I did in the previous exercise, I forgot to pay attention. Let's see, here's the next premise. Does it say we can use that for a conjunction? No, let's see if it accepts it. Those were our only two premises, and the conclusion is CT. Let's see if it likes this one. It's in first order. I guess it will indeed accept the horseshoe or the actual arrow instead of this arrow, and it will accept the conjunction symbol that comes on the keyboard in place of that one, which is good because that makes it easier. Okay, so, oops, I don't know what I pushed there. Looks like there's lots of other buttons that you can probably get comfortable with. So it looks like this is a new line. This is a new subproof. This is finish a subproof and start another. This is finish a subproof and add a new line. We'll play with those in a future thing. This is new to me too, so. Okay, let's do our proof. And again, if you haven't already, pause and do it again. Or pause and do it now. that you've seen it and see if you can do it without looking at the answer now that you've seen the answer, if you didn't already do this. Okay, so let's just quick check it in our proof checker. Step number 1. Just gonna copy and paste this. We're taking the universal quantifier off. We're going to replace all occurrences of the bound variable with one term. In this case, I'm choosing t because that's what's in the proof elsewhere, and that's in the conclusion. Okay, and we got to justify it. Where's our justification? That's weird. I don't know what is happening. Let's remove it and see what happens. Oh, I think I somehow started a subproof, and you don't justify the first step apparently in this. I accidentally clicked a button. I knew I did something wrong. Okay, so let's start over. Okay, and what's our justification? It is line 1, universal instantiation or universal elimination. What's our next line? Simplification, right? So let's do line 2. What are we calling simplification now? We are calling it, either name it simplification or call it the conjunction elimination. You had a conjunction, now you don't. So conjunction elimination. And I wonder if it will accept this. I bet it does, given it accepted the other one. Yep, and it replaced it with simplification, so that looks good. And not dt, line 2, simplification. Let's do and elimination. Now what can we do? We've got these lines here for modus ponens. So I'm going to cite lines 3 and 4 and arrow elimination. And now I have a disjunction and the negation of one disjunct. So I'm going to put the other disjunct on a new line and cite lines 5 and 6. What are we calling disjunctive syllogism now? Where is it? Oh, that's right. Here's another weird name for disjunctive syllogism, modus tollendo ponens. But luckily this one is just DS, like we've been calling it all along. And that's the proof. Where's check proof? Well, I don't enjoy that in my demoing the thing, it appears not to be working. That's very annoying. We'll just assume that it was good and hope that was a fluke and try it on the next one, because I'm not going to troubleshoot this while on the video. I will troubleshoot it after and hope I just had some weird fluke. At any rate, we'll see how helpful the proof checker is. Maybe it won't even work well. Okay, so now that we've seen 2 examples, I've said what the rule was and showed you how to use it. Here's a formal, like, clear statement of the rule. I recommend that you make a new cheat sheet for yourself. I gave you one before with all the rules from propositional logic. Now I recommend that you make your own. You could also skip ahead to chapter 16 in the book, and there's one there. But what I recommend you do is write down the rule in English. That's your number 1 reference. And then if the schematic helps you, maybe that's helpful to have too, but recall that in this case, this capital phi, this Greek letter, could be any statement. We've now looked at 2 different, here is a universal statement that's super complex. Here's a universal statement that's less complex, right? Both of those would fit this schematic. And if this schematic is all Greek to you, no pun intended, then maybe write down some examples that use the rule for reference where you realize that it will apply to other examples similarly. But this is the main rule. If you have a universally quantified formula, main operator is the upside down A on its own line, then you can remove that quantifier and replace each of the bound variables with any term, and then write the result on a new line. And then you justify it by citing the line that had the quantifier in the first place and the rule universal instantiation. Okay, here's one more. I recommend you pause and do it on your own, as well as try it out in the proof checker. And hopefully it will work. You're going to need some numbers. So here's line 1, and here is line 2. Okay, let's do it together. What do we see? Here's the conclusion. And I notice the conclusion is the consequent of a conditional. And I know that modus ponens is a rule that allows me to get on a new line the consequent of the conditional if I have a conditional statement. What I would need in order to use modus ponens in addition to a conditional statement is the antecedent of that conditional. I would need to have this on its own line. If I had this on its own line, I could use modus ponens to get the conclusion. How will I get this on its own line? Well, look, this looks an awful lot like it. There's a P and there's a Q. There's just no A. How am I going to get there? Can you apply universal instantiation to this line in the proof? No, you can't. Why? Because the main operator and or quantifier is not the universal quantifier. It is a conjunction. So you're going to have to simplify it and get those universally quantified conjuncts on their own line. So I'm going to just copy and paste these. There's one, and I'm going to kind of do both at once. Okay, and how am I going to justify this? Line 1, simp. Line 1, simp. Okay, now I can use universal instantiation on both of these lines. What can I do? I'm just going to copy and paste it. The rule says remove the quantifier and then replace the universally bound or the bound variable with whatever you want, any term. And let's pick A because obviously that's the one we want given the other premises. So what do? We cite line 3 and we cite universal instantiation. And then we'll do the same for line 4. We'll remove the quantifier and put in a term, cite it. Oops, this time it's line 4, same rule. Okay, we're getting closer. We're trying to get this on a line. Now we have two things on a line. What do? We put them together with the conjunction rule. And that is going to be lines 5 and 6. And conj or adjunction, or what else could we call it? So here's adjunction, or what we've been calling conjunction. And the shortcut for this is, so just like E, we said stood for elimination, I stands for introduction. So if you've introduced a conjunction, this is called conjunction introduction, conjunction introduction, or conjunction or adjunction. Sorry, it's what to call the rule is the most complicated thing here. And that's unfortunate. So you could call it, and it won't make you use the little caret, so you could call it this. Like I introduced one of these. We didn't have one before and now we do. So it's conjunction introduction, or just regular old conj if you're writing it up. And now we can use modus ponens. So final step is WA, and the rule is 2, 7 modus ponens. Okay, at this point, if you want to end the tutorial video, feel free. I'm going to redo this in the proof checker. If you didn't pause and do this on your own, I recommend that you now pause and do it on your own, or do it in the proof checker without, you've seen it done, but now can you do it on your own, quasi from memory, quasi working through it. Okay, so step number 1, I'm going to put And my premises. And the conclusion is WA. Create problem. Oops, I'm not in first order again. Okay, new line. Simp. What do we call that? We call it and elimination. This is our new rule. Remove that quantifier. Now I'm going to put them together. We'll call this lines 5 and 6 and conjunction introduction. And finally, modus ponens gets us to the conclusion. That's 2, 7, arrow elimination. Congratulations, this proof is correct.